Right, so I already covered the very first part of 0.5 with using the calculators. We're going to finish it off by talking about the graphs of sine, cosine, tangent, and then their reciprocals. At the very end, we'll also cover like a trig identity, but we'll start with this graphs. Right, so it says trig functions are periodic. What that means is they repeat themselves, and they have a certain period or cycle. So they have a certain pattern every so often, whatever the period is, it will start repeating itself. Sine, cosine, and tangent have a period of 2 pi. So think of you, if you're doing those circular functions, you're going all the way around the unit circle, they'll repeat themselves every 2 pi. Whereas tangent and cotangent functions have a period of pi. The easiest way to graph these, and you guys are already familiar with the graphs, so I'm not going to go into too much detail, but the easiest way to graph them, especially with sine, cosine, cosecant, and secant, is just to use the points 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then knowing that they're periodic, we can kind of graph the rest of it from there. So that's mainly what we're going to focus on. We're just going to do a really light sketch of it, and then we're going to do transformations. When you're doing tangent and cotangent, we'll actually use pi over 4 and negative pi over 4, because that will be helpful to us. Okay, so let's get started. So we're going to start with sine and cosine. So if I'm starting with sine, I want you to think of the unit circle over here. Right? If I'm at 0 degrees, that point is 1, 0. Remember, the sine is my y-coordinate. So since the sine of 0, my y-coordinate is 0, that's my first point right there. When the angle is 0, I get 0. If I come up to pi over 2 up here, that point is 0, 1. So again, the sine is equal to the y-coordinate. So at pi over 2, right here, it's equal to 1. Okay, keep going around here. If I get over to pi, that point is negative 1, 0. Again, the y-coordinate is equal to 0, so I'd be back to here. 3 pi over 2, which is down here. That coordinate is 0, 1, 0, negative 1, excuse me. The y-coordinate's negative 1, so I'm back down to here. When I get back to 2 pi, I'm back up to here to this point right here, so my y-coordinate's back to 0. So again, you've seen the sine function before, but it's a smooth curve. It looks like this, right? It's curving up, hits that point, curves down, hits that point, curves up. If I keep going, right, if I go another half pi, I would just end up right back up there again. So I'd end up back up at 1. And if I keep going, I get back to 0, and you can see it just keep repeating itself. We can actually go backwards. Let's go backwards. If I travel this direction to negative pi over 2, my y-coordinate is negative 1. If I keep going around to negative pi, that put me right here. My y-coordinate is 0. I go to negative 3 pi over 2, that would be up here. My y-coordinate is 1. And then I get back to negative 2 pi. I've gone all the way around and back to 0. So it's just going to keep repeating itself. So we said at the beginning that our period is 2 pi. So from 0 to 2 pi, it goes through one complete cycle and takes us back to where we started. And like I said, this shouldn't be like new or crazy for you. You've seen it before. A couple side notes. We call the distance from here to the center or from here to the center, like that distance right there or that distance right there, it's the same. We call that the amplitude. So in that case, the amplitude of the original sine function is always equal to 1. We said the period is equal to 2 pi. So it repeats itself every 2 pi. Okay, the cosine function also has a period of 2 pi, but it's the x-coordinate over here, right? So let's come back over here, and we've already got our unit circle drawn. Let's just find all the x-coordinates. So at 0 right here, the y-coordinate, the x-coordinate, excuse me, is 1. So at 0, you start at the peak of the cosine, its highest point. When I get to pi over 2 up here, the x-coordinate is 0. When I get to pi, my x-coordinate is negative 1. When I get to 3 pi over 2, my x-coordinate is 0. And when I get to 2 pi, I'm back to 1 again. So I'm back up here at 1. So it's actually the exact, if you remember, it's the exact same shape as the sine. It just starts at a different location. Okay, so it starts at its peak. The sine starts in the middle, right? At that point, 0, 0. The cosine starts at its peak. Hey, let's go the opposite direction. If I go backwards this way, When I get to negative pi over 2, which is right here, my x-coordinate is 0. So a negative pi over 2 is going to be 0. If I go to negative pi, which is up here, I can go all the way up to there. My x-coordinate is negative 1. I go to negative 3 pi over 2, and I get 0. And I go to negative 2 pi and back up to 1. So you can see how it keeps following that same pattern. So sine and cosine are the same graph. In fact, if you take the cosine and shift it, do a horizontal translation, or the sine, you can make them match up perfectly. Take just a second, see if you can figure out how far you would, so pause it, figure out how far you'd have to shift or translate left and right the sine to make it look like the cosine. This is pi over 2, right? So if I shifted it to the left, pi over 2, right? I take this part and shift it to the left, pi over 2, it would match up exactly with the cosine function. So if I actually take this function, we know how to do that translation. If I went to sine, y equals the sine of x minus or plus pi over 2, because I want to go to the left, that would actually make it, you could put that in your calculator, the cosine, y equals the cosine of x and y equals the sine of x plus pi over 2. They'd be the exact same graph if you shifted it over. Okay, what we're going to do is we're going to use the graphs of the sine and cosine to draw the graphs of the cosecant and secant. So I'm going to leave that sine graph up there and use the cosecant graph to draw it. So if I come back down here, remember the cosecant is equal to 1 over the sine. So what I can do is I can take those points and I can take the y-coordinate and flip it over. So when the angle is 0 right here, if I take 0 and take the reciprocal, I end up with 1 over 0. What that means is this graph is actually, that doesn't work, right? So the cosecant is actually undefined when your angle is equal to 0. If I take this high point, oh, let me do it in a different color. If I take this, so I took 0 and took the reciprocal, it's undefined. If I take 1 and flip it over, I get 1 back, right? 1 over, I take 1 and flip it over, it's still 1. If I come over to pi, at pi, the sine is equal to 0. Well, when I flip that over, I'd end up with 1 over 0, so there's another vertical asymptote. Let me just switch this. We'll do everything the same color. Okay, so at pi, there's another vertical asymptote. Okay, and if you think about what happens, as my y values get smaller, if I take those and flip them over, if you take 1 divided by a smaller and smaller number, you get a bigger and bigger number. So what actually happens is this graph comes up and just goes along. It goes along those vertical asymptotes like that. Okay, let's see what happens as I go across. If I go to 3 pi over 2, at 3 pi over 2, the sine's equal to negative 1. If I flip over the negative 1, I get a negative 1 again. If I go to 2 pi, it's equal to 0 again. At 0, you're going to have another vertical asymptote, right? It's going to be 1 over 0. As I come along here, I'm getting smaller and smaller negative numbers. If I flip that over, 1 divided by a really small negative number is going to give me a really big negative number. So it's going to be down here like this. So the way I draw cosecant is I always draw the sine first. So if I were asked to draw this, I'd start, well, I know what the sine function looks like, right? It looks like this. And everywhere it gets to its peak, it's going to share that point. And everywhere it's equal to 0, I just put a vertical asymptote across there. So if I kept going with the sine function, it'd be a point here, 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 and here. It looks like this, right? So I'm going to call it every time it's equal to 0, I'm going to put a vertical asymptote coming down. And every time it's equal to 1, I'm going to have it just come down and connect. So by drawing the so the cosecant function is that green one. If you draw the sine function first, then it makes it easier to draw the cosecant function. And you could do the same thing for the cosine. So to draw the secant, I'm actually going to start by drawing the cosine. We just did that up above, but here's my points. So it looks like this. Okay, so every time the cosecant equals 0, let's do this one in red. Every time the cosecant equals 0, there's going to be a vertical asymptote. Every time it equals 1, you're going to have that graph. There's going to be another vertical asymptote right over, whoops, wrong spot. there's going to be another vertical asymptote right there. So that graph's going to be curving this way, and it's going to be curving down this way. Then I could keep going with the cosine function, right? It crosses here, there, there, there. So right here, there's going to be another vertical asymptote. Right there, there's going to be another one, another part of the secant graph there. So you could, by drawing the sine and cosine function, you could draw the secant and the cosecant function really easily. Hey, we said the period is still 2 pi. That's still true. If I look at it, right, I have to go, it starts here, I go down this way, then it comes down here and goes that way. When I get back over here, it's going to start over again, so it's going to be up here. So from 0 to 2 pi, it goes through one period. So the period of both these functions is still 2 pi. That's true of sine, cosine, cosecant, and secant. Cosecant and secant do not have amplitude. The amplitude is like the height of the curve, like how far from the center it is. Well, these graphs keep going up forever both ways, so there is no amplitude on those. Okay, the last two graphs are tangent and cotangent. So I'm going to kind of think about, I'm going to see if we can, we're going to make this table here and just kind of see what happens. So we'll use that same one. I've got 1, 0. I've got 0, 1. I've got 0, negative 1. And I've got negative 1, 0. Okay, so if I start with the tangent, at 0, the it's y over x, right? Tangent is equal to y over x. So I take the 0 over 1, which is 0. Okay, if I go to pi over 2, which is up here, I go y over x, I get 1 over 0. Hey, that's undefined. So at pi over 2, there's actually a vertical asymptote. It doesn't work. At pi, right here, if I go y over x, that'd be 0 over negative 1. There's another point, it's 0 again. If I go to pi, over here, excuse me, if I go to, oh, I'm sorry, it only goes to pi. So let's move this point over. So at pi, it was equal to 0 again. Okay, if I go the opposite direction, if I go down to negative pi, down to here, I get negative 1 over 0, which is undefined. So negative pi over 2. Let's go on that way. Okay, and here's what happens. The graph comes up like this. It comes along this vertical asymptote. It curves this way. It hits that center point, and then it's curving up that way. So that's what the tangent graph looks like. And we could find more points, right? We know it crosses at pi again, so it comes up this way again. It's curving up that way. There'd be another this is negative pi over 2, there's a vertical asymptote. At pi over 2, there's a vertical asymptote. If I go over pi again, at 3 pi over 2, there'll be another vertical asymptote. And at 5 pi over 2 and 7 pi over 2 go on both directions. So there's our tangent graph. Now I want you to notice it repeats itself between negative 1/2 pi and positive 1/2 pi. That's pi. So the period of this graph, period is 2 pi. It does not have an amplitude. Again, the amplitude is how high or how low the graph goes from the center. Well, that graph keeps going up and down forever. Okay, let's do cotangent. Cotangent is really similar. So if I start at 0, this time it's x over y, I'd have 1 over 0. So this one has a vertical asymptote that actually goes right along the y-axis. At pi over 2 up here, if I go x over y, be 0 over 1, be right there. And at pi over 2, it's undefined again. Excuse me, at pi, it's undefined. Oh, man, I'm struggling here, sorry. At pi over 2, it's equal to 0. And then at pi, it's undefined again, right? I would get negative 1 over 0, which doesn't work. Okay, cotangent looks just like the tangent, except it's a decreasing function. So it actually starts up here, comes down, hits that point, okay, and it's curving down that direction. Now we could, that's one period right there. We could do another one over here. Every pi, there'll be one. So there's one at 0, a vertical asymptote at pi. There'll be a vertical asymptote at 2 pi. There'll be a vertical asymptote at negative pi. It'll cross halfway between that, and it's just a decreasing function. So you just got to remember the tangent is always increasing, whereas the cotangent is always decreasing. So you got to know where the vertical asymptotes are, and you can do that really easily if you're not sure by either picturing that in your head or drawing that unit circle on there, you can figure out really fast where the vertical asymptotes are and where it's equal to 0. And from there, just remembering the tangent's always positive, got positive slope, it's always going up, and the cotangent's always negative. Hey, the rest of the assignment is just doing transformations. These transformations are exactly the same as all of our other transformations. So A is a vertical stretch. Now, if you look down here, because A is a vertical stretch, it changes the amplitude of the graph. So on sine and cosine, it makes, if there's a 2 in front, instead of going up 1, it'll go up 2 to those peaks, to those high points, to those maxes. The C on the inside moves you left or right. The D on the outside moves you up or down. That's the same thing as we've always done. B is still a horizontal stretch or compression. So that controls the period. So think horizontally. If I squish it in, that's going to make the period smaller. If I extend it, it makes the period longer. So the way we find the period on all of them is we take the original period. So for sine and cosine and cosecant and secant, the original period is 2 pi. I always divide it by the absolute value of b. So if there's a negative 2 in there, I'd go 2 pi divided by 2. Or if there's a half in there, I'd go 2 pi divided by a half. Now remember that the original period of tangent and cotangent is pi. So for those, I take pi and divide it by b. So if you look on here, like the amplitude, it does mention there, right? There is none for the tangent, cotangent, secant, cosecant. So most of these transformations are the same. We're using a little bit different terminology. We're using period for the horizontal compression, squeeze or stretch, and we're using amplitude for the vertical stretch or compression on the sine and cosine. But for the most part, the transformation is exactly the same as we've done in the past. Now, one thing I do want to point out in here is before you decide what C is right there, you've got to make sure B is factored out. And I'll show you an example of that. So let's do a couple of graphs. So that first one says we want to graph a -5 cosine of x over 2. So identify what everything is. So on this one, A is equal to -5. And B, I'm timesing by a half in there. So B is equal to a half. So think about how that's going to affect it. If A is a -5, it's going to affect the amplitude. So instead of being the amplitude of 1, the amplitude is going to be 5. Because it's negative, it's also going to reflect it vertically. So normally the sine function starts going up. This one's going to start going down because of the negative. It's reflected across the x-axis. Because B is a half, take the normal period, which is 2 pi, and I divide it by B. So 2 pi divided by a half. Well, when you divide by a half, it's the same as multiplying by 2. So 2 pi times 2 means the period is equal to 4 pi. Okay, so I'm going to do my cosine function, excuse me. I said sine, so cosine will start at the peak. So I'm going to start actually, normally I'd start at 5 because that's my amplitude. Because it's been reflected across, I'm going to start at -5. And I know when I go through one period, over at 4 pi, it has to be back to that point. So it's got to be back to -5 right there. Because those are the maxes, halfway between will be a min. So at 2 pi, there's going to be a point at +5. Halfway between those 2 points, it's going to cross. And halfway between those 2 points, it's going to cross. So it's going to look something like this. Okay, we're not looking for perfection. We just want the general shape. Obviously, mine's far from perfect. That's one period. It said to do 2 cycles or 2 periods, so let's keep going. If it's down at -5, at -4 pi, it has to be back there. You have to complete one cycle. Halfway in between, it has to reach its peak, and then it's going to cross halfway between those. So you can draw another cycle, looks something like that. All right, this one, g of t equals a sine of 2t minus pi over 2. So this is one you got to be careful with. Before you decide on that horizontal shift, because there's a minus pi over 2, you've got to factor the 2 out. So I've got to take a 2 out of both of those. So if I take a 2 out, I'd have a t left minus. And if I want to take a 2 out of there, when we're taking a factor of 2 out, we're dividing by 2. So we're going, what is a half divided by 2? So what's half of a half? And that's a fourth. So it's going to be pi over 4. So my horizontal shift is actually pi over 4. This 2 is going to change the period. Right, it's b, so I go 2 pi divided by 2, the original period, which is 2 pi divided by 2, which comes out to be pi. So it's going to repeat itself every pi. What I'm going to do is I'm going to graph the sine function without the horizontal shift, and then I'll add the horizontal shift in there. So if the period is pi, sine function starts at 0 in the middle, and it ends at pi. It's got to go through one cycle. Halfway in between, it will cross again. Halfway between there, it'll reach its max point. Halfway between there, it'll reach its midpoint. So this is what the original graph looks like. Now it said we got to shift it right, pi over 4. So my final graph's going to look like this. If this is pi over 2, pi over 4 is right here. So I'm going to shift over to there, shift that one over to there, shift that one over to there, shift that point over, that point over. So the whole thing is just shifted slightly that direction. And we can keep going. If there's going to be another point there, another point there, and another point there. And then we're going to have a max point there. You're just repeating the same thing, right? Oh, wow. I didn't do well on that. I went the wrong direction. So this point, right? If this is my one, if it crosses here, it's got to be right here. It's got to be the next one. Sorry about that. Now that looks right. Now I've got 2 cycles of that. So make sure you factor out the 2 before you decide on your horizontal shift. And a lot of times, like we talked about before, transformations, I would do one step before you do the other one. Hey, the very last thing, it says sine cosine functions are related to each other using Pythagorean identities. You may or may not remember this from last year, but if I have the sine squared plus the cosine squared, it always equals 1. So the sine squared of an angle plus the cosine squared of the same angle equals 1. And right, it doesn't matter if it's x's or thetas. So example 5 says, use the Pythagorean identity to rewrite this, so that I only have one trig function, and then we want to solve it. So right now I have sines and cosines. So what I'm going to do, up here, right, if sine squared plus cosine squared equals 1, that means the sine squared of theta equals 1 minus the cosine squared of theta. So I'm going to take this and substitute it in for the sine squared. So I would have 2 cosine of theta minus, and in place of that sine squared, I'm going to plug in 1 minus the cosine squared of theta equals negative 2. Okay, I'm going to distribute that through. I want to try solving this equation. So I have 2 cosine of theta minus 1 plus cosine squared of theta equals negative 2. This looks hard, but I'll show you how we can do this. Let's rearrange things. I'm going to put the cosine squared first. So I have cosine squared of theta plus 2 cosine of theta. And then I'm going to add the 2 over with that. So it ends up being plus 1. So this is kind of weird, but this actually is a quadratic. See the cosine squared plus 2. So if I think of it as being x squared plus 2x plus 1, that factors to be x plus 1 times x plus 1. So if I want to factor this, I can. It will just factor to be cosine of theta plus 1, cosine of theta plus 1. So normally I'd set both of them equal to 0, but because they're the same thing, I don't have to do it twice. I'll just do it once. Okay, now I want to solve that. Okay, so we talked about like how do we solve this? Well, we could try doing it by hand, but this one actually doesn't work well by hand. So instead, I'm going to take this y equals the cosine of theta, because we can use a calculator. Sorry, it's supposed to be cosine of theta plus 1. I'm going to take this and graph it, and I just want to find out when it's equal to 0. I can't use my calculator up on here, but you would just sorry about that, Bill. But you just go into y equals, you would graph this. When you do that, if you hit the zoom button, the very last option is a zoom trig, and that sets it up really nice so you can see the trig function really well. Make sure you're set to radians, like I talked about in my other video. And then you're just going to find the zeros. Now remember, there's going to be a lot of zeros. This cosine function is going to cross a touch a bunch of times. We're only looking for the ones that are between 0 and 2 pi. So you just use your calculator to find those. If you have any questions on that as far as graphing it and finding the zeros, it's what we've done before. The only difference is you're doing with a trig function, and you have to make sure your calculator is set to radians. If you have any questions on that, let me know, and I can kind of guide you through that. Thanks, guys.